So far in our energy unit, we've talked about potential energy due to gravity and kinetic energy due to a speed or a velocity. We've also talked about work and how work can be added to a system to either add or remove energy from that system. Today, we are going to add one more type of energy that's going to be important, and that is elastic potential energy. You've probably experienced this. You've ever stretched a rubber band or a spring or even compressed a spring. Inside your pen, you might have a spring that you compress when you click it. Those are all ways of storing elastic potential energy. Now, in order for us to calculate this form of energy, we need to understand a bit more about how you can calculate things from a graph. And this is something that we've done before, but we've had pretty consistent axes to our graphs. We're going to start changing those up depending on what we're trying to find from that information. So say we have a velocity versus time graph. This is something that we saw in our force unit, and we calculate the slope of that graph. Now, the slope of the graph is just the change in y divided by the change in x. And what's useful about that is then we can then plug in some units and figure out what is that quantity actually referring to. So change in x, y over change in x is my velocity divided by the time. So velocity divided by time is meters per second divided by seconds. Meters per second can be written out as meters per second squared, and that is our unit of acceleration. So knowing that we have the slope, we can understand that the axes are basically just dividing. So the velocity, the y-axis, divided by the time is our meaning of that slope. Well, the other thing that we did in a graph is we found the area bounded by a curve. In this case, the area bounded by the graph can be calculated by essentially multiplying these two axes together. In this case, there's also a 1/2 in there because it's a triangle, but overall, in terms of the properties, they're going to be multiplied instead of divided when we're finding the area. So now we have the velocity times the time. In terms of units, that's meters per second times seconds. The seconds would just cancel out and give you meters. Meters is our unit for displacement. So in this case, you can figure out in a couple different ways, either using the properties, velocity divided by time or velocity times time, or using the units that result, meters per second squared or meters, to figure out what is the slope or the area telling you about this particular set of data. Today we're going to look at a different graph, one that uses force and distance rather than velocity and time. So here, to make this graph, let's look at a very simple setup. Let's say that you pull or push this block with 40 newtons of force, and you allow it to go the entire distance with a very consistent force. And say we push it from 2 meters all the way to 8 meters with 40 newtons of force the entire time. We can see that again. And notice down here in this force versus distance graph, we're just presenting 40 newtons the entire time. So the force is not changing. And from 2 to 8 meters, actually this is probably more representative of displacement, between 2 and 8 meters, we are showing that force. Now, that would result in an overall distance of 6 meters. So we've got a force of 40 newtons applied for 6 meters. From that, we should be able to calculate the work. If you remember, our calculation for work is force times displacement times the cosine of the angle if the force is at a different angle to the motion than 0 degrees. But in this case, it's in the same direction, so we're just going to say force times displacement. Our force is 40 newtons, our displacement is 6 meters. That is basically calculating the area of this graph. So the area here, 6 meters times 40 newtons, or vice versa, will get us 240 newton times meters. Well, that can be simplified to just saying 240 joules. Our unit for work is in joules. Calculating the area of a force versus distance or force versus displacement graph will give you the work being done by the system. Well, this is great if it's consistent like that, but a force isn't always consistent. And our equation breaks down a little bit because this definition only really works for either a constant force or an average force. So now we're going to deal with that average a little bit because sometimes the force is going to vary. If you pull a spring or a rubber band, as you're stretching it, it requires more and more force to continue stretching it. So you might be able to pull it maybe 1 centimeter with a little bit of force, but the next centimeter requires even more force, and even more force, and even more force. So as you're stretching it, your force is changing because the rubber band is pulling back on you stronger the farther it's stretched. The way we can represent this is to either do a simple lab or see it in a simulation. In this simulation, we have a spring here that is hooked up to a force probe. That force probe is being read out here in newtons. And if I start, I can pull that spring and see what happens to the force. As I'm pulling it, the force is getting larger and larger and larger. If I wanted it to stay constant, the force would just stay constant there if I just wanted to hold it. But if I want to continue stretching it, the force gets bigger. So I can represent that on a graph with the x-axis being the stretch, basically the distance that I've pulled it, and the y-axis being the force. And notice this graph is not consistent the whole time. Unlike that graph that we just saw that was 40 the whole way, now we are getting bigger and bigger, starting at 0 and growing as we go. Now different springs will result in different graphs. So notice here this one's slightly steeper. I can try it again, and it's less steep. So the things that we're going to care about here are how far we stretch it and the force that's resulting from that stretch. So before we look at a specific example of a spring, let's return to this idea of using the area to find work. So say now that my force is not constant the whole time, and instead it starts at 0 and then increases the farther the distance is applied. So now we need a different method. We can't just multiply force times distance, because what force would you use? In this case, this overall force is showing up at 20 newtons. Here it's 10 meters. And I could find the area is 1/2 10 meters times 40 newtons, base 1/2 base times height, to find a total area of 200 joules. So the work being done here is 200 joules of work. And I can find that by using the area rather than just a general formula that we have. Well, it turns out that we can actually use a formula as well. But first, let's look at this in terms of an actual spring. So say we have a spring here and we pull it down. Such a cool animation. We pull it down and we see that the force gets larger the farther we pull it. And this must be a very large spring because it's being pulled a distance of 6 meters. So we can see that again. The farther I pull it, the bigger the force becomes. Now, we are generally going to use an overall distance here of 6 meters. So we have a final force of 40 newtons and a distance being pulled 6 meters. Go ahead and calculate what is the work being required to stretch that spring. So again, all we're doing here is we're using this area under the graph, our area bounded by this graph. So 1/2 6 times 40 will give you 120 joules. So as I mentioned, in physics, it's nice for us to have a formula every once in a while, rather than having to do a graph in order to find something that maybe doesn't match with what we were doing. To find this formula, we need to understand that this pullback distance is increasing. So as the pullback distance increases, we are increasing the amount of potential energy. So that's kind of a general idea. So you've probably experienced that before. If you've pulled back a rubber band, the farther you pull it, the farther you're able to launch it because you have stored up more potential energy. Well, it turns out that this idea of a force being larger as you stretch a spring is a pretty consistent concept and actually has a formula to represent it. We call it Hooke's law. And that formula is basically just saying the force is equal to some constant K times how far you stretch the spring. So the farther you stretch it, that delta X, the bigger the force has to be. Now this K value has a special name. We call this the spring constant, and it is a property of the spring. If you have a really small spring, K will be fairly small, which results in fairly small forces. If you have a really heavy spring that's hard to pull, you'll get a really large K value just because it's resulting in large forces. Now, K has a unit in order for the units to work out, because force has a unit of meters, or force has a unit of newtons rather, and delta X we're going to measure in meters. So K has units of newtons per meter. It's basically the slope of your force versus distance graph. And I want to point out here that this delta X, it isn't the length of the spring. Instead, it's the distance that you've pulled it from its resting position. So that delta X is how far from its resting position has it been either stretched, or you could compress it from that resting position and measure the distance from equilibrium there as well. So then, if we have this formula, we can calculate what the spring constant is with a very, very simple sort of lab. Here we have our spring. Normally, let's say it's a 4-meter spring, and you put a 2-kilogram block on it. You hang it from the spring, and we notice that it stretches to 8 meters. I want to find what K is. In order to find K, I need to know the force, and I need to know the stretch distance. Well, the force is going to be the force of gravity here. This is a 2-kilogram mass. Force of gravity is just mass times gravity, so 2 times 9.81 will give me 19.62 newtons of force being applied to that spring. We also need to know how far it stretches. Again, the stretch, this X, isn't going to be 8 meters. It's not the total length of the spring. Instead, it's going to be how much did it stretch from before we actually applied a force, and that answer is 4. So the delta X, the change in our stretch, is 4 meters. So we plug those in. 19.62 is equal to K times 4. And you can find that K is about 4.9 newtons per meter, which means that for every new meter that you pull, you're going to have to pull another 4.5 or 4.9, almost 5 newtons than you were the meter before. So for the first meter, it requires about 5 newtons. Second meter requires about 10, 15 to stretch to 3 meters, and so on. So this comes back to this idea of work and energy, because the work done on a system causes the system to either gain or lose energy. If you are applying work to a spring, stretching or compressing it is storing energy in that system. So if you pull back on a rubber band, you are storing potential energy inside that rubber band. You're applying a work, you're working on the rubber band to store that energy as elastic potential energy. Same thing is true if you're compressing a spring. So like a pinball machine, if you pull the plunger, you're actually compressing a spring inside that plunger and storing energy that way. So when you release it, it can get converted into kinetic energy and cause the ball to move. So let's generalize this in a formula that doesn't require the graph. So we know that force is some spring constant times the change in X. So we now calculate how much energy is stored in that system. Say we have our force versus distance graph again, with our final force, our biggest force being F, we'll call it F. Well, in that case, there is some average force here. In this case, it's half of that F value because we started at 0. Well, if I want to find the work, remember that this equation can only work if you have a constant force or if you're using the average force. So here we're going to use that average force and say, okay, the average force is just 1/2 times this final force. And I'm using this instead of just F because the force is changing. I'm not at F the entire time. So my average is just 1/2 that. Now, S is going to be the change in X in this case. And force, we know for a spring, is K times delta X. K times the change in X. So I can simplify F into this equation for the spring, Hooke's law. And I can change S because the distance that I am traveling is how far I've stretched it. And that can be simplified down to 1/2 K delta X squared, because delta X shows up twice. This is the work that I'm putting into the spring as I stretch it. And it's also the energy that the spring is storing. So we call that the elastic potential energy. So these two equations are going to be really important. The force is not actually given to you in your data booklet. The reason I'm presenting it here is because that's what gives K some meaning, that spring constant. But what you're going to see in your data booklet here is 1/2 K delta X. So let's see what that looks like here. Now our three types of energy that we know about are these three here. And this first one is if you have a velocity, you have some kinetic energy. The second one that we talked about in our previous video is if you have height, there is some force of gravity. PE, we're going to add a little subscript G to say it's gravitational potential energy. And then now 1/2 kx squared is the elastic potential energy. The variables that IB physics uses here are a little confusing, I think. I'm going to use this KE, PEE, and PEG to represent elastic and gravitational potential energies. So if we look at this in terms of a conservation of energy problem, how far up a 15-degree incline of a pinball table will a 0.1 kilogram pinball move after it is launched? The spring constant is 100 newtons per meter and is compressed by 0.08 meters or 8 centimeters. So same as what we did before, the initial energy has to equal the final energy. Now we have another form of potential energy to include in here. So looking at our situation, we start with some elastic potential energy. We've compressed that spring a certain amount and stored up some energy. We're going to use this as our starting height. So we're going to say no gravitational potential energy there. And it's not moving, so there's no kinetic energy. At its highest point, this final, we basically just have gravitational potential energy based on the height that it is, the vertical height, which doesn't actually care about the angle that this pinball has traveled up. So that means that this equation can be simplified greatly because there's no kinetic energy or gravitational potential to begin with, and then there's no kinetic or elastic potential to end. We are measuring the height relative to its starting point, so only the final has potential energy based on this equation. So we have 1/2 K delta X squared is equal to mass times gravity times height. There isn't a mass in both terms, so we can't cancel anything further. We can just plug in what we know. So 1/2 times K, 100 newtons per meter, times the compression here, 0.08 squared, is equal to 0.1 times 9.81 times the height. Plugging those in, I can find that the height is about 33 centimeters or 0.33 meters. So just as we did before, now we just have one more form of energy that we can add to this idea of conservation of energy, converting from one to another. We can also look at this in terms of work. So how much work is required to stretch a spring with this spring constant, 200 newtons per meter, from 0.1 meters to 0.4 meters. So if I find my initial energy and my final energy of this spring, I can figure out how much work there was required to change from one to the next. So my initial is 1/2 times 200 times 0.1 squared. That's just 1 joule. My final energy is 1/2 times 200 times 0.4 squared, 16 joules. The delta in between here, the amount of energy that was added to the system, is 15 joules. As we talked about before, work is our way of adding the energy to the system. So if I want to know the work, that is 15 joules. That's how much energy was added to the system with work on the spring. Well, you can look at this equation or this problem here and make one very common error. We can look at this and say, okay, it stretched from 0.1 to 0.4. Why wouldn't I just say, what is the change in this stretch? So instead of saying 0.1 and 0.4, why would I just say 0.3? Well, it turns out that there is a major reason why that doesn't work. If I were to do 0.3, I would end up with 9 joules, which is different than what we calculated before when we were looking at the difference between 0.1, the energy in 0.1 and 0.4. So the reason that this is different, we can see in the graph. If I were to look at this just as we're stretching at 0.3, the graph would look something like this, according to this K constant here, with a slope of 200. We would get an area of 9 joules, so 0.3 times 80 divided by 2. Now, if I wanted to find what actually happened here, I would find that the force is actually changing here. As it's going up from 0.1, the force would be 20, to 100 here at 0.4. The starting force isn't 0. So the area here includes everything up until that 0.1. So you're requiring actually more force for that whole time. And the area under this graph is 15. So it is very important that you are looking at the difference here. And now I'm looking at this now. The area isn't actually... Yeah, no, the area is... That's right. So that means that you cannot do this stretch. So one more example here. Let's look at this increasing the force on a metal wire, and the wire extends from an initial length L naught to a new length L. The graph shows the variation in force for the length of this wire. The energy required to extend the wire from L naught to L is E. So this energy here would be E. The wire then contracts to half its original extension. What is the work done by the wire as it contracts? So we'll call this E nu. And so that's my new energy. What I'm looking for is, what is the work being done by the wire as it contracts? How much is it different here going from E to E nu? What is the overall amount in that difference? Well, looking at this, we don't have any numbers here for our force, but you can look generally at what this triangle would look like. If I have half the base here and half the height, I have a quarter of the overall energy. So really, this is like saying E minus 0.25 E, which results in 0.75 E. So 75% of the energy is lost in compressing this halfway, which means that is the work that's being done by the wire to remove that energy from the system. So overall, our takeaways here: you should be able to calculate work as the area bounded by a force distance graph. You should be able to look at Hooke's law to calculate the elastic force of a given displacement, and then describe and calculate elastic potential energy, how it's used for a conservation of energy problem, but also how it's used in a work energy problem. So adding work to the system to stretch a spring for a new energy based on its old energy.